so our learning objectives for today, we're going to evaluate logarithmic functions. Graph logarithmic functions. And use basic log properties. So a log function is just the inverse of an exponential function. And you can switch from exponential to logarithmic with the following formula. And the way I remember it is I always think this little guy down here, he doesn't like being on bottom, he goes and he pops up that other guy. So I always think of like a big uppercut coming over. So it goes around the x because you're uppercutting and it pops the y all the way up. So then you're left with that a popped up the y, and then the only thing that's left is that x. So let's see if we can't switch back and forth between log form to exponential form. So right here, if I have log base 10, that 10 is going to come around, pop up the 3, and the only thing you're left with now is 1,000. And is that correct? Yeah, 10 cubed is 1,000. So what if it was in exponential form? How would you get backwards? Well, this is what's really nice. Whatever your base is here, the base is also the base of the log. So as you're going backwards, it helps to remember that. So here 2 is my base, so I know the base also has to be 2. And then I think, well, what did he come over and pop up? The 2 popped up the 4, so it goes there. And then what's left? The 16. So then one more time going the other way, this 3 comes around and uppercuts. And that is true. So now it wants me to actually evaluate, and we're going to do this without a calculator, so completely all by hand. So the first thing I do is I say, well, it's going to equal x. I'm evaluating it. I want it to equal something. So I'm going to set it equal to x. I'm going to take the 3 and let it go pop the x up. And then 3 raised to the what is 27? Well, that would be 3. So let's do the same thing. So 10 raised to the what is 10,000. Well, that was 1, 2, 3, 4 zeros. So x would be 4. What's that? 64. All right, so this one's a little bit, oh golly, sorry about that. Silly smartboard just threw me off. All right, so 64 is bumping up the x, and that's going to equal the 4. Okay, so this one's a little bit harder to tell. The way I do it is I try to make this face maybe look similar to this face. So all I'm going to do is rewrite 64 as 4 to the power of something. Well, that would be 4 cubed. So now I can see that 3x has to equal the 1. So x is 1/3. Another way to see that is you could have said the cube root of 64 is 4. So a lot of you could see that there. Okay, some properties of logs. Whenever you have 1 going on, no matter what that base is, you're always going to get out 0. If you think about that, it'd be a to the 0 equals 1. And that's true. No matter what your a is, you're always going to get 1 if you raise it to the 0 power. Okay? A and A, when you have the same base, logging the same thing on the inside, you're going to get out 1. And if you want to see that again, a to the first would be a, regardless of what your a is. When you have these guys going on with an exponent, same thing, you're just left with x. And again, when you have the same thing going on here, you're left with x. So let's see if we can do these examples. On A, I have this inside as 1, so no matter what the base, I know I get out 0. B, 31 and 31 are the same, so I get out 4. Here I have 4 and 4, it's raised to that first power, so I get out 1. And here the 10 and the 10 are the same, so I'm going to get out 5. Alright, now the fun stuff. We are going to graph logs. Well, if you look in your calculator, you don't have a log base 4. So you can't go to y equals and put log base 4 of x anywhere. So we're going to have to use what we just learned about the inverse functions of an exponential function in order to graph the log function. So the first thing I'm going to do is go find the inverse. So I know that I have to switch my x and y when I go find that inverse. Now I need to solve for y. So if it's in log, the inverse is always going to be in exponential form. So let's go have that 4, pop up the x, and now I have what y would be. Once I have the inverse, I'm going to make a table. So I'll get some values. At 0, I'm at 1. At 1, 4 to the first is 4. 2, 16. So let's go the other way. At negative 1, 4 to the negative 1 would be 1 over 4. To the negative 2 would be 1 over 16. This is not what I want to graph. I'm going to use this now to graph my log function. And how I'm going to do that is I'm going to flip-flop the x and the y's from the inverse. Because inverse is the domain and the range switch. So I can graph these points now in red on my chart. Alright, so let's see if we can describe this a little bit. The domain is going to be, it doesn't ever hit 0, so it's going to start at 0 and go to infinity. My range actually hits everything, negative infinity to infinity. So your asymptotes, you have a vertical asymptote. Whenever you have logs, you're always going to have a vertical asymptote. So you'll have a vertical asymptote with your logs. And here it's just x equals 0. And the way you can find that is whatever that inside is going to be, you can set it equal to 0. And here you can see, when you go to graph, that yes, this is at x equals 0. Let's do another one. Now I have to first subtract my 1 and divide by the negative. And now I can bump it up. So I need to get that log isolated before I bump it up. Make your chart. So again, I know my vertical asymptote is here just where x equals 0. So I'm going to flip-flop. And graph these guys. So it looks like you're going to have a horizontal asymptote, but you don't. It's just going to go very, very slowly, but it will eventually keep going all the way down forever and ever and ever. So my domain is from 0 to infinity, but my range is still all real numbers. All right, common logs are the logs with a base 10 and base e. And you actually have these two in your calculator. When the log is a base 10, you don't have to write it, just like you don't have to write if you multiply by 1. It's just kind of known. And so you can just write log of x. That means you have a base of 10. When you have the log base e, that is the ln of x. It is the natural log of x. And these are the only two in the calculator. Okay, so let's look at these few and see if we can't evaluate using that natural log. So anytime I see an ln, it might help you if you write it log base e to know what's going on as you start to solve or evaluate. So now I see I have the same base, so I'm just left with 22. So I'm going to rewrite this guy as e to the negative 4 so I can see the same base, and I'm left with 4. This guy doesn't have anything special going on, so it is still just the ln of 2. I can't rewrite that in any way that's nice. So domains, again, we talked about in the domain that inside of the x has to be greater than 0. For both of these guys. So whatever's going on the inside, it has to be greater than 0. Your range is always going to be all real numbers. And you can always kind of look in the calculator to see when you have the base 10 or the base e. So you cannot have a non-positive number inside of a log. It has to be greater than 0. So let's look at this first one, find the domain. Well, I know this inside of the log has to be greater than 0. So when I go to solve that, I get a domain from negative infinity until 4. So let's find the domain of this guy. All right, Brooke, these were your favorites. So we're going to factor and set it equal to 0. And I get to make my true-false chart. Yay! So pick a value before and after. So I'm going to pick -1, half, 2. And let's go plug that in. So if I had -1 minus -1 squared, is that greater than 0? So that would be -1 minus 1, and that is false. That is not greater than 0. Try a half. So this would be a half minus a 4, and that is true. And what about 2? That would end up giving you 2 minus 4, and that is false. That is not greater than 0. So I can see now that this is where it was true from 0 to 1. Okay, let's do an application example. A certain strain of bacteria divides every 3 hours. If a colony started with 50 bacteria, then the time in hours required for the colony to grow to N bacteria is given to me by this formula. And it says find the time required for the colony to grow to 1 million. So here I know that I wanted to grow to 1 million. Since this log is base 10, you can put it in your calculator, and you should get approximately 42.86 hours. Make sure you can do that. Okay, let's try this next one. The rate at which a battery charges is slower the closer the battery is to its maximum charge, C naught. The time in hours required to charge a fully discharged battery to a charge C is given by this formula. So K is a positive constant. And then it tells me that K is 0.25. When the battery is fully charged, how long will it take the charge to 90% of its maximum charge? So 90% divided by its fully charged would give me 1 minus the 0.9. So fully charged is at 100%, which is 1. So plug that into your calculator, because you do have ln, and that will take about 0.58 hours. All right, one more. This one's kind of fun. Which is larger, log base 4 of 17 or log base 5 of 24? You can think, oh no, I don't have a calculator that does log base 4 or 5. So we get to use our brains. So log base 4 of 17, let's let it equal x. I'm going to go switch it to something that I can see a little bit easier. Look like that. Well, let's go through some powers of 4. Where would 17 fall? Somewhere in there, right? In between 4 squared and 4 cubed. So I know x has to be between 2 and 3. Well, let's look at the other one. So now I'm going to go through powers of 5. Where would 24 fall? Right in here. So I know this x has to be between 1 and 2. So the output we said was x, and this one has to be between 2 and 3. This guy has to be between 1 and 2. So which one is bigger? Log base 4 of